Hello and welcome to the webinar. If you have any questions throughout the webinar, please use the GoToWebinar questions box and type them in. They will be sent to Vibration Research and someone will answer your question as quickly as possible. A copy of the slides can be downloaded through the GoToWebinar interface.
My name is Joel Minderhout and I'm a research scientist at Vibration Research, and I'll be presenting today's webinar on analyzer functions. At Vibration Research, we're committed to our 6 core values. These 6 core values are innovation, do the right thing, collaboration, capable and competent, strong and driven work ethic, and accountable and responsible. Today's presentation on analyzer functions, what we'd like to do is show you where in the Vibration View software you can find the analyzer functions. On the right here is a picture of the key settings that you might have turned on, and here's the analyzer function key. It's a add-on package that's pretty important, and sometimes it's overlooked, and it would be valuable to have. And so that's part of the goal of this presentation, is to also show you what the analyzer functions communicate and what possible use cases there might be for the analyzer functions. So let's first of all look at where can we find these analyzer functions in the Vibration View software. And I'm going to be flipping back and forth between the software and the presentation. Today's presentation we are using the newest 2018 software, and this is a sign test that I happen to have open, and we'll come back to this in a moment. If we take a look at the analyzer features, you're going to find them available in the sine, random, and shock test modules. And what you're going to find is that these are special plots or special graphs that are available to you. And those 4 particular graphs and plots that are available to you are the transfer function, the coherence plot, the cross spectrum plot, and the total harmonic distortion plot. Here are a couple screenshots of the software. On the left is a sign test and the tabs that are available to you when the analyzer key is turned off. And you'll see the various tabs that are available. But when we turn on the key, when you purchase that analyzer feature, you get a few additional tabs. One is the pretest tab and the other is the analyzer tab. Now, we could spend some time talking about the pretest options that become available to you with the analyzer. That's not the goal today. Today we want to talk about some of the particular graphs that are available. So we're going to focus our attention on, in the sign test, what's available under the analyzer tab. And if we take a look at that, there would be the swept THD that needs to be clicked. And I just want to make sure to emphasize that when you have the analyzer feature, this swept THD is not turned on by default. You have to manually turn that on. If you don't, you will not be able to access the THD plots. So it's very important that you turn this on when you run a test. The other thing that's important is how many analysis lines you've chosen. And a little later in the presentation, we're going to run a test live and show you what happens when this value is not very high. But the Analyzer tab is the new tab that's available in the Analyzer features in the sign testing. And when you get to your graph settings, when you don't have the Analyzer key, these are the graphs that are available. But with the Analyzer key on, there you'll see the THD is available where it was not available before. And there are a couple other graphs, the scatter plot and the spectrum plots. Again, for sake of time, we're not going to today get into the details of the scatter plot or the spectrum plots. We're going to focus our attention on the THD. That's in sine. In random, when the analyzer key is on, you get three other unique graphs: the cross spectrum plots, the transfer function, and the coherence plots. And our goal today is to talk about those four graphs: the THD and the sine, and the cross spectrum, transfer function, and coherence plots in the random test settings. It is also available in, the analyzer features are also available in Shock, and they would be seen here as the transfer function and the coherence plots. So what you're going to have is any test that involves sine or random or shock will have these four graphs available when you have the analyzer features, and therefore transient captures or tests that involve shock or sine of one sort or another will involve these graphs. So all across the board, you're going to be able to use them in the Vibration View software. But what would these tools be used for, one might ask? Well, anytime you're trying to compare the relationships between two signals, then these analyzer tools are going to be very, very helpful. So think about situations where you have two signals that you're trying to see how they relate. The analyzer tools will be useful. So you should have the analyzer package anytime you are involved in comparing relationships. And generally the two things that you compare in those relationships are amplitudes and phase differences. And so the picture here is showing a situation where I have a multi-axis triax Excel that is monitoring some vibrations, and you'll see the transfer function and the amplitudes of these plots, as well as the phase differences between channel 2, for example, and the reference of channel 1. So anytime you're interested in the amplitude and phase changes and how those relationships occur between two signals, the analyzer tools will be helpful. That means that analyzer tools are going to be very helpful in any situation where you're doing multi-axis testing. The whole multi-axis testing world would be interested in the analyzer tools because you have vibrations going on in different axes, and you're interested in knowing how those vibrations relate. And some of the tools in the analyzer package will be very helpful in that situation. But it's not just the multi-axis world that would be interested in the analyzer package. Single-axis systems would be also helped by having and using the analyzer tools. Two examples. If you were doing shaker validation testing, you want to know how the shaker head is performing, then comparing some of those relationships using the analyzer tools would be good. Also, any other pre-test evaluation of the system, of the shaker and its product, would be good examples of where you might use the analyzer tools. But what specifically is communicated by those tools? There are four important graphs: the transfer function, the total harmonic distortion, the coherence plot, and the cross-spectrum plot. What do those four teach us? What are you learning when you are looking at those graphs? So let's start with the transfer function. Transfer function, very similar to what we might be familiar with as the transmissibility plot. We'll talk about the difference in that in just a minute, but the transfer function compares the ratio of the PSD values for two signals across a specific frequency range. So in this particular case, I have a shaker system, and I have a cantilever beam with a mass on the end. And I may be interested in knowing how the vibration at the end of the beam compares to the shaker head. So in this case, the channel 2 is at the end of the beam. Channel 1 is the head of the shaker. And how did those compare? Well, this beam is going to have a resonance at some point, or multiple resonances. And we see that in this plot. The channel 2 amplitude vibrations differ significantly from the shaker head. If they were moving exactly the same with the same amplitude, then this vibration and the head's vibration would be the same. So you would have a value of 1 across the board. But we don't have a value of 1 across the board. We have peaks at various locations because of resonances in this cantilever beam. And not only does the transfer function show you the comparison of these amplitudes of these PSD values, but it also shows you the phase relationship between the two signals. So we can find out whether or not the end of this beam and the shaker head are moving up and down at the same phase. Are they in sync, or are they out of sync? Are they out of phase? And for example, at say about 350 hertz here, the end of that beam is about 130 or so degrees out of phase with the vibration of the head of the shaker. At other places it's 90 degrees out of phase, or minus 90. So you're seeing that the beam and the head are not always vibrating in phase. So the transfer function would be a tool that you would want to use to compare in what way are the end of the beam and the shaker head vibrating in terms of their phase and their amplitude. Transmissibility accomplishes much the same thing, but transmissibility, which is a standard feature in all the software, does not give you the phase information. So when you want to know some things about the phase, you need to have the analyzer tool. So transmissibility will give you some of the amplitude information, but it does not give you phase. So phase is very important in many situations, and so it would be good to have the analyzer function so you can have access to that phase information. Total harmonic distortion is the second plot that we want to focus our attention on. It's in the analyzer package. It's a measurement of how well the shaker recreates a signal from the controller. When there's the whole system, the amplifier and the controller and the accelerometers, there is going to be some harmonic content that is found in the signal, and that harmonic content distorts the sinusoidal wave that we're trying to generate. And so you're interested in knowing how much distortion has occurred, and the software calculates the next 10 harmonics of a particular frequency and determines how much harmonic content is there compared to the fundamental. And the more harmonic content there is in that signal, the greater the total harmonic distortion is. And so total harmonic distortion is a tool that's going to be helpful in comparing the control signal and the excitation signal. In other words, how pure is the output? Other ways to ask that question would be to say how much noise is in your signal, or how much undesired vibration is in the system, or to what extent has the sine tone generated by the controller been affected by the noise of the amplifier and the shaker. And the plot we have in front of us here is showing that the two signals that are being compared differ greatly in their total harmonic distortion. This green plot was the shaker head when all was working properly, but if you had a loose bolt on the head expander and there was some warping and vibrating of that head expander, then you did not get a nice replication of the control signal, and there are things that are out of whack, as it were, in a lot of frequencies. And so there was a very high total harmonic distortion at these other frequencies, indicating something's not quite right with your system. So total harmonic distortion is another important tool in the analyzer package. Third, there is the coherence plot. Coherence is a plot of the correlation calculation across the frequency domain. If you make this plot, the two signals are determined to be coherent if they would have a constant phase difference and if they have the same frequency and the same waveform. So in this particular plot, there's a comparison of channel 2 to channel 1, and for the most part, there is correlation between those two signals. But at this particular frequency, there is not a very good correlation, and therefore the plot for coherence is much below 1. And that signals to you that at that particular frequency, there's either a difference in those phases that's not being kept the same in the phase vibration of the shaker and the product, or their frequencies and waveform are not the same. So what is plotted is a value of either something between a 1 and a 0. If you have a value of 1, that can teach you a couple things. There's a good relationship between the input and the output, and that may be a good indicator that there's good control. So if your controller is doing its task well, then you should have a coherence value of a 1. If the value is low, close to 0 or a value of 0, then there's very low output signal, and it may be indicative of very poor control or of some other issues. And so the coherence plots can be very helpful to help identify, is there an error in your instrumentation, a loose cable, or some other problem with the instruments so that you are not getting good coherence? Or is it possible that there is an inconsistent excitation? Is there some problem with the shaker that it's not vibrating the system as it's supposed to in a consistent way, and you will not get a good coherence value? Finally, it may be indicative that your controller is not doing its job properly, and so coherence is a good tool in those ways. Here's an example. In a particular test I ran, I compared channel 1, which was the head of a shaker, with the drive signal. And you can see that the control is excellent. All the way through, the value is a 1. So it says that the controller is performing very well. These little hiccups here are because of resonances that were present, and therefore the feedback made it so that it was a little difficult to control at that particular frequency, and yet this coherence value is relatively close to 1. So even through a resonance, it was performing well. In this particular case, we compared channel 2 to the head. So this was at the end of a beam, and we would expect, of course, that at the end of the beam where there are resonances, that we're not going to get the same kind of vibration or the same kind of phase information as you would at the head. So you would expect coherence values to be much further away from 1 at various locations. So some tools available when you're dealing with either control evaluation or even in a multi-axis situation. Finally, the fourth tool in the analyzer package is the cross spectrum plot. And again, here's another plot that helps compare one signal with another in time. The cross-spectral density contains data regarding both amplitude and phase differences of the two signals. And this is very helpful when you're looking at multi-axis testing. You want to know, for example, in the situation that we're going to run in a few minutes live, here is the vibrations of channel 1, and here's the vibrations of channel 3. And at certain frequencies, we are trying to excite channel 1, and we're finding that we are getting large vibrations in a completely different axis than the one we are trying to excite. And this is very informative. It tells the test engineer that in this particular test, at certain frequencies, another axis is being excited than the one we were intending to excite. So what we've done is ran a couple tests to demonstrate the use of these. I have the screenshots of these in this PowerPoint presentation, and then I'm going to move to the live software and show you some of those things. A couple tests we did. One is with this little mini turbine blade, and we ran a sine sweep, as you would typically do, to find out where the resonances are of that turbine blade. And in the sine test that we ran, we did plot the transmissibility. Now remember, transmissibility is not a analyzer function. It's a standard feature. But I just show you this because when you run, most people would use a transmissibility plot to find the resonances, and you would annotate those resonances and calculate the Q factors and annotate them right there on the screen. But what the transmissibility plot does not do for you is it does not include phase differences. And so the analyzer feature of transfer function is better than the transmissibility plot because it's going to give you the ability to see the phase differences. And that's very important to look at. And if you do not have the analyzer feature, you're going to be excluded from that information. So anytime you're doing some single axis testing in which you are trying to evaluate your shaker, or you're trying to troubleshoot for test or system anomalies, or anytime you run a sine sweep to identify resonances, you're going to want to use the transfer function. And it's superior than just using the transmissibility because the transmissibility doesn't have the phase data, and it's more influenced by the noise than the transfer function is. So you'd be wise to have the analyzer feature to have the option to use the transfer function. Total harmonic distortion, as we already said, measures the harmonic content. We ran two different tests here. On the left, you'll see a head expander, and we're trying to exhibit here what might happen if there was a loose bolt in this head expander. Here's an accelerometer near the center, and we put some on the corners to see how this corner vibration is, whether it's different or not than at the center. And when we ran the test, this green line would represent the vibration of one of these accelerometers on the corner when there was no wrench placed on the head expander. But when I put the wrench on the head expander, then the wrench vibrated and bounced around, and that would be analogous to having a loose bolt, let's say, and the whole head expander then was influenced by that vibration of the wrench, and it was picked up, and the total harmonic distortion was much greater over a certain frequency range than when the wrench was not present. And so in this particular case, you are trying to excite a similar vibration in the corners as you would at the center. You're expecting to have the same kind of vibration. And if you expect to have the same vibration, you should have a low THD. That would be your goal. And if it's not, it's going to show you some problems. And so this is a very, very helpful tool when you're doing shaker validation testing, or if you're doing fixture mapping, or screening the product for some problems. You would want to use the total harmonic distortion plot. We also try to test with multi-axis vibration. We set up some rather strange configurations just to test out our system to see what we could get. And here is a triax Excel, and at the end of this mass, and you would expect this rod to vibrate up and down, and the whole system should vibrate up and down. The question would be, would there be any motion in that axis, or would these weights make the end of these masses vibrate down and up? And so is there different kind of vibrations going to occur? And here I would expect high total harmonic distortion, because when I'm running the test, I'm, for the most part, not expecting motion in any other axis. Okay, so I'm not going to get similar signals. If this thing is vibrating in a certain way, I'm not expecting the other axes to have that same vibration, so I'm expecting total harmonic distortion to be different. And so across the frequency range, there is a difference between them, but there are places where they actually yield similar THD. And that would mean that when they're giving similar THD, that the vibrations are actually in the other axis quite similar to the kind of vibration that's happening at the head. So it could be a tool used in multi-axis testing to identify when one axis is actually performing similar to the axis that you're testing. So there's an example of total harmonic distortion and where we might use that. And we summarize them here. Anytime you would be maybe doing shaker validation testing to identify noise or to evaluate the health of your shaker system. If you are evaluating the ability to control through a resonance, if you're trying to assess problems with the device under test and whether there's any unwanted vibrations in it, those would be all single axis type test situations. But also if you were running multi-axis tests, and are there vibrations in one axis that affect the vibrations in another axis, that would be a good use of the total harmonic distortion. In coherence, as we've already said, you're comparing how much of the output signal is due to the input signal, and we can evaluate therefore the ability of our controller to do its work. It's also helpful to evaluate the health of a shaker. And just as we've shown in some of these other plots, it would be helpful to evaluate how the vibrations in one axis affect another. So anytime we are interested in the quality of control or any possible instrument errors, that one's a big one, because I did a test once and had a loose cable. In fact, I think the cable was damaged, and the results just weren't what we were expecting. And when we looked at the coherence plot, that was the plot that was very helpful in identifying there's a cable issue here, and or something, some kind of instrumentation issue, because everything else seemed to check out. And it was a plot that helped us identify that. Cross spectrum. How are my vibrations in axis 3, for example, affected by the channel 1 vibrations, and at what frequencies, and with how much effect. And therefore, in multi-axis testing, we can use the cross-spectrum plots to evaluate those situations. So what I would like to do is run through a couple examples on the software and show you some of the slides that I've taken screenshots of previous tests. Here I have them in the presentation. I'm going to try to duplicate them. For example, in a single axis test, I've already talked about this shaker head situation. Right now on my shaker is this apparatus that we're using for some other testing. And so since it's on the shaker, I just want to show you again how you might use these 4 graphs to learn a few things. In this case, just a single axis test. I know this is a triax, but if we just compare its up and down vibration to the up and down vibration of the shaker head, might be kind of like this. If I had a full head expander, how is the outside corners vibrating compared to the center? Let's see how these vibrate, and are they in sync, and what kind of coherence values you get. So for example, here's a total harmonic distortion plot of this vibration, and we're going to go to, well, I'll just make this comment before we go to the software. All the way across the frequency range, we have a total harmonic distortion of basically 1. This is the channel 1, and that's just evaluating the shaker head here, and we would expect that the total harmonic distortion is low. There is a little hiccup here, and that's because of a resonance that we find in channel 2. There's a pretty large resonance here, and that resonance, as it vibrates, if it does, because it's attached to the head, this vibration will affect the shaker head a little bit. And so the feedback that channel 1 is giving back to the drive is that there is this vibration, and so the controller tries to compensate, and you'll find that then there's a little bit of issues controlling through that resonance, but not bad, and the total harmonic distortion is not terrible, but it is a higher value here, so it does indicate something's going on. Let's go take a look at the software and run a test. Here's a sine test that I have previously ran. Notice just for now that total harmonic distortion at about 200 hertz all of a sudden plateaus at 100. I want to show you what's going on here. Let's edit the test. We're going to run a 3/4 G peak from 20 hertz to 2000 hertz, and we're going to sweep down from 2000 and a sweep rate of 2. And let's go to this Analyzer tab. I have the swept THD on, but the FFT lines were low, 2048. That's what I just ran on this previous test. And because the value was so low, the THD was not, this is really junk data here. We aren't getting good values because the FFT lines are so low. So what we want to do is increase those FFT lines. Let's bring them to as large as we have available, 32,768. And if we apply that and run this test, we're going to see that the THD is going to be valuable across the rest of the spectrum. So just a reminder that when you are running a sine sweep, to make sure that you go to the Analyzer tab and click on the swept THD. This is normally unclicked. That's the default. You need to click it to activate it so that you'll have access to these graphs. So we're going to run the test a minute. This is in our new 2018 software. This may look slightly different than the software that you have available. We encourage you to upgrade, and So the test is running on a shaker outside this room. I can pick up the sine sweep audibly, but you might not be able to pick it up. But the THD is being calculated. Here's transmissibility. Now we could change that graph a minute, and instead of doing the transmissibility, we do let me back up a minute here. Just leave that alone. I want to watch it because it's going to hit a frequency here, and sometimes on this particular test struggles to get through this one because we're sweeping a little fast. So I'm going to change the sweep rate to 1. Apply that a minute. Helps me get through this resonance here. So while we're on the fly, we can change the sweep rate. We're going to go back to, in fact, I'm going to change it up to 3 so we can finish the graph a little faster. Now I got a lot of channels open here, and it's making the graphs look kind of complicated. So I'm going to turn off a couple of these channels so we can just focus on one of them. I'm mostly interested in the channel 3 because I would expect some channel 3 motion there. So I'm going to turn off the channel 4 and channel 2. We'll keep the channel 1 on so we can see how that compares, and we'll do that for all the channels. Just taking a look at what is happening in these other channels. By the way, notice that the THD on that previous test was quitting at about 200 Hertz, and now we are getting THD values all the way across the board because we increased the FFT lines. So we would expect that the THD of channel 1 would be a 1 all the way across. And remember, we showed you this one peak. This is that peak because there's a resonance here that we're having a little trouble controlling through. And we can see that resonance on the transmissibility graph and on the acceleration profile. But channel 3 is showing us that that other axis is has quite a high THD. We would expect that. We wouldn't expect that channel to have the same kind of vibration as channel 1, but there is a few places where the THD lowers and it becomes similar, and the transmissibility graph is showing us that there are some activity on that other axis influenced because of the vibration of that shaker head. So there's an example in the sine testing of the use of THD. Let's take a look at a random test. Flip back to our presentation a moment. In the random testing, we can look at the coherence plots, and we can look at the transfer functions and the phase. So we're going to take a look at those at this time in live software. We're going to run a test here, 10 Hertz to 1000, and it's a flat spectrum random test. Run the test, start it over, and in this particular case I've got all the channels open. Let me close those because the goal here was just to show how we might use this in a single axis situation. And I'm not interested in channel 3 and 4. I'm just interested in the head of the shaker, channel 1, and the vibration in the end of that beam, also in the same direction. And we would expect that those would be relatively the same, although there are some resonances in channel 2. So we'll let that run a minute. If you take a look at the situation here, you would expect, kind of like here, that the center and the corner are going to do the same, unless there's a problem here. And there's no problem here that this has got a resonance. But if this was part of your whole shaker head or so, if you were to get some results like this, that would show you that there's some problems with your system. Here we have resonances at various locations and correspondingly coherence values that are not 1. Now you might notice that these don't match up with the resonance. They actually match up with the anti-resonance, because the signal is so low at the anti-resonance that the signal is not matching the shaker head. And so you're going to get a correlation value that is indicating that there's not a good relationship there. And so there's the coherence plot and a cross-spectrum density plot showing how the two axes are not always matching. We would expect them to match in this particular example. Here are locations where they are not. And as far as transfer function is concerned, if we edit the graph, we can maybe change this one to the transfer function. Apply that. You can see the transfer function. How channel 2 compares to channel 1 in terms of amplitude. If you want to take a look at its phase, we can add another graph. And we'll put the transfer function phase in there for those two. And so you'll see that the phases are matching for much of the frequency, but then there are places where at this resonance there's a phase difference of about 180 degrees out of phase, and there are phase changes of different values elsewhere across the spectrum for that channel 2 as it compares to channel 1. And that information is not available if you were only using transmissibility. So there's the software being used. Stop that test a moment. We'll go back to our presentation. Using that same setup, we could make a comparison in the multi-axis world, where we're going to compare THD, cross-spectrum, plots, coherence, transfer function, and phase. I ran the tests, and you just saw me running those tests. In fact, if we go back to the software, if I go back to the sine test, and if we open the data for that last test, I want to show you that when you access that data afterwards, you can still see all that data. And if notice the channels aren't all on, but if I edit the graph, I could put channel 4 and 2 back in and do that for the graph 3 here. And that data all comes back and available. And you'll notice that the channels, 2 and 1 were supposed to be kind of matching, but you would not expect THD of channel 3 and 4 to match with channel 1. And here's an example of the THD of channel 3 compared to channel 1. For the most part, those are not matching. We weren't expecting vibrations in channel 3 to match channel 1, so you expect there to be a total harmonic distortion that's different. That's if you're in the sine realm. If we go to the random world, the plots of coherence teach you some of the same things, and the plot of the transfer function phase, or the transfer function, if we just take a look at that a moment, channel 3 and channel 2 are not matching, except for here, channel 3 has a resonance, and in this area here, about 300 hertz, we're seeing some motion in the channel 3 axis that is similar to some of the vibration in channel 2 world. So that means that the energies that are being brought by the shaker intending to excite a resonance in channel 2 are also exciting a resonance in channel 3. If we go back to the coherence, we find that there is quite a bit of coherence difference, particularly in this range, all indicating that channel 3 is not having the same kind of signals as channel 1. So those are a couple graphs and the cross spectrum plot. Again, in the multi-axis world, if you are interested in knowing how the various axes interact, this is a good plot to use. We're trying to excite a resonance in channel 2, but at the same time we are seeing at various locations that we are exciting resonances in the channel 3 axis. We did this same demonstration with this, what we call pendulum test, this mass, and we would expect some vibrations in the various axes. And so we ran the test, and here we have plots of the THD of all 4 channels. When all 4 are on, it becomes a little messy, but you can, with the different colors, identify how the various axes are comparing. The same is true with the transfer function and its phase. And I did in this graph look at phase of channel 2 to channel 1 and channel 3 to channel 1, channel 4 to channel 1 in different plots, keeping the channel 2 and channel 1 in each graph just so you have a comparison how they were looking. And here the cross spectral density as well as the coherence for all the 4 channels. And you'll notice that for the most part channels 3 and 4 are not behaving the same as channel 1 and 2. We would expect channel 1 and 2, go back to the plot or the picture, I would expect channel 1 to be doing the same kind of vibration as the up and down vibration of that triax, and that's what you're seeing. You're seeing that there is similar vibration, and the other axes are not having the same vibration, except for in 1 or 2 locations they have something similar. So I hope that this presentation helps you understand a little bit better the features of the analyzer functions, the 4 plots, transfer function, total harmonic distortion, coherence, and cross spectral density. And those are tools that are available in that analyzer package. They're very helpful in multi-axis testing, but also available and helpful in single axis testing where you might be doing system checks or shaker validation testing.